Okay, we are now going to transition into our tangent lines and be looking at some uses for that. And again, we can approximate our tangent line using the slope of our secant line, and we're going to look at that as well. Something for us to keep in mind is that these 2 points here, the first point, the point of tangency at A, F at A, and the slope at the point of tangency denoted F prime of A. Notice there's a difference there, and those are two different y values. And then notice what's inside the box. Any function with a defined slope at a specific point will have one and only one tangent line at that point. Very important for us to note all of that. The other things above here are very important as well, and I will leave that for y'all to read. So in the first examples, they want us to draw using a straight edge, and I don't have one, so we're going to do the best we can. We are going to draw the tangent lines beyond the point of tangency in each direction. And this is good practice for us, just looking at particular points here on our graph. So drawing in these tangent lines, the whole point of this is for us to keep in mind that when we draw our tangent lines, we are only intersecting the graph in at most one point. And so notice that there's several different types of tangent lines here. And again, as we go around the function, if you'll note that when the function is increasing, the slope of that tangent line is positive. Whenever our graph is decreasing, the slope of the tangent line is negative. And notice whenever we're neither increasing nor decreasing, that our slope would be 0. So those are important for us to keep in mind. And again, as we're drawing these, it is important for us to take note when that slope would be positive, when the slope would be negative, and how is that relating to the original function as well. And this one's really strange here in figure 2 because again, you've got some really strange graphs here that you can make points of tangency, and you could really technically here, if we wanted to, we could even draw in here. We would only hit at one point, and we would only cross here at one point. So that's going to give us some interesting information as well for us to look at. And again, y'all can finish sketching a lot of these. I think y'all have the right idea, so we're going to move on. Okay, now we need to answer some questions here. And you can look back at your examples if you need to. So here, how does the position of the tangent line in the graphs at example 1 and the lines of the graph example 2, or I'm sorry, example 3, relate to the concavity of the function? So here, when it talks about concavity, you're either opening upward or downward. That's what the function is doing. So for part A, when the curve is concave up, the tangent line is actually below the curve. So that's something that will come back into play. And if you are concave down, then your tangent line is above the curve. And if you're at a turning point here, then the tangent is 0. Or you can also say that it is horizontal. At a point of inflection, and I know we're not sure just yet with point of inflection, that's where the graph changes shape. So here where it changes shape, now it does not change directions. That's going to be here, this turning point. This is where we change directions. So let's go ahead and note that as well. We are changing directions up here. All right, so if we're changing concavity, so then that means here at that point of inflection, then we have a vertical tangent, or the slope of that would be, or well, the vertical would be undefined, or we could also say a 0 as well. At a sharp corner, or cusp, the tangent does not exist, and we'll go into a little more detail for that. And at a point on the function, the tangent is of the same slope as a line. And so that's where we're coming in with this local linearity. Okay, now we're going to write those equations of the lines that we've graphed. And so the two things that are so important for us to have in order to write these lines is we need an ordered pair. Now back in Algebra 1, we call that ordered pair x and y. But now we're going to transition that to be a comma f at a. And then we also need a slope of some sort. So our slope, m, we're now going to call that f prime at a, which is going to be the derivative value at a. We can also associate, well, that a looks like a 9. Let's make that an a. That can also be the derivative value. We're saying that and we're like, what in the world? Well, all of that means is our instantaneous rate of change at x equals a. That's all it means, is our instantaneous rate of change. Now let's look at the forms that we could possibly write our equation in. One form is going to be your traditional y equals mx plus b. And you don't see that used as much, but it could pop up. But the most used form is y equals our slope, but instead of m, I'm going to put f prime at a times x minus a. And then notice we're going to have plus our f at a. That's going to be the new way that we write it, just so that we know right here is really our x value, this is our y value, and this is our slope. And we really need to memorize this form. This is going to be very useful for us. Okay, so our next part, it says using figure 1, estimate the slope at each of the points and use this information to complete the table below. So at point A, I believe we have the point -5, -5. If we estimate the slope, then we're going to have a slope of 5. And now we have everything we need to write the equation of the tangent line. So y, and we really probably should start that out with f of x. It's going to be interchangeable, but you'll see f of x more so than y. So f of x equals our slope times x minus a. So minus the -5 is +5, and then plus a -5 or -5. At point B, we would have a slope of 0. And that ordered pair there would be -1, 3. So look at what our equation of our tangent line would be now. Our slope is 0. And then we would have x minus -1, so plus 1. And then we would have plus 3. So really, you're not going to see all that written out. You're going to see really all of that simplifies just to be f of x equals 3. All right, and so now let's look at part C. Part C, the ordered pair there was 1, 1. Our slope we can estimate to be 3/2. And so here we could have our function f of x. It's going to be equal to, and our slope here was 3/2 times x minus 1 and then plus 1. So notice how we need every single part of that in order to do our equation of our tangent line. So finally, notice they want us again to rewrite our equation, and we will. Again, this is the big equation that you should always use. And again, it's going to be f prime at a times x minus a plus f at a. Very important for us to remember that formula. You will use that throughout the entire year and on the AP exam. Okay, I have intentionally skipped over to example 6 because this is getting a little bit more into what we need. Now, here we've got a radical function, y equals the square root of x, and then they've given us f prime at x. So this is going to be our slope generator, and that's important for us to know there for sure. That means that this little equation is going to find the slope of any and every tangent line along the graph. Very important for us. So notice in example A, it says the slope of f of x equals square root of x at 9. So we're finding that slope there. And they tell us that f prime at x is equal to all this. So what we need to find would then be f prime of 9. So that's going to be 1 over 2 times the square root of 9. So that's going to be 1 over 2 times 3. So that's going to give us 1/6. And then it tells us to write an equation for the local linearization of f at 9. So what that means is just writing the equation of the tangent line. So that wording is really strange here. So let's go ahead and say, okay, that means that I need the equation of the tangent line. That way we can go ahead and distinguish very quickly what it's asking us to do. So now with that, I need A and I need f at A. I need these two things. And then I need also f prime at A. So I have our A value. That's right there. F prime at A is right here. So there's my f prime at A. But I don't have my y value or my f at A. So that means I need to go plug back in to the original. So I need to find f at A as well. So I'm going to have 9 comma, and then f at A is going to be the square root of 9. And so that ordered pair is going to be 9 comma 3. And then my slope that I need, that slope value is going to be 1/6. So now I have everything I need in order to write the equation of that tangent line. So we're going to have our line, or our function, is going to be 1/6 times x minus 9 plus 3. So there's our, let's see, what did they call it? Local linearization. All right, so now it says using your results from C, estimate a value for the square root of 9.1. So keep in mind this line that we just wrote, the f at x equals, let's see, it was 1/6 times x minus 9, wasn't it? Yep, x minus 9 plus 3. That's going to give us a pretty good approximation. Now this was going to be for, keep in mind, this was for the function f at x equals the square root of x at the point, and our point was 9 comma 3. So we need to keep that in mind. So really the x value is not the square root of 9.1. It's going to be what is underneath the radical. So x is 9.1. So really all this is asking us to do when it's asking us to estimate this value, it's wanting us to find f at 9.1. Well, we just wrote a great equation for that. And so we are going to sub in, and we're going to have, let's see, 1/6 times, in place of x, I'm putting 9.1 minus 9, and then plus 3. So we can find out that f at 9.1. Now on the AP exam, don't go any more than this. This is plenty to, after you've substituted in. But here, if we wanted to keep going to do a pretty good approximation, it would be 3.0166. if you typed all that in your calculator. All right, now in part D, they want us to graph the function and the tangent line at x equals 9. Now the square root function, hopefully we remember what it looks like, but if not, it's okay. We're just going to go through here picking some nice numbers. Well, I'm going to pick 0 because I know the square root of 0 is 0. I'm going to pick 4 because the square root of 4 is 2. And let's choose 9 because I know the square root of 9 is 3. And let's see, how much further does this go out? Let's go ahead and pick on 16 because the square root of 16 is 4. So notice that we have this function. This looks like the good old square root function. And then notice we have the tangent line that they wanted us to find. That tangent line was at 3, what was it at? 9, 3. So let's go over 9 at 3 right here. And so we could approximate here the slope of this line. That slope of that line, we found that to be 1/6 is what we found. So that's pretty good for us to keep in mind. Let's see what else we've got to answer here. Okay, so for part E, it says to explain whether your answer to C is an overestimate or an underestimate for the actual value of 9.1, and justify your answer by reference to the behavior of the graph of f at the square root of x. Well, this, let's see, think about where the graph was. We had a graph that looked like this, and then our tangent line was sitting above that. So notice that the tangent line was sitting up here. So that tangent line is a little bit higher up than the actual function itself. So it's going to be an over approximation, but how do we put that in the math terms so that the Sheldon Coopers of the world will grade it correctly? Well, we would start with f of x is what we call concave down. Because it's tilted over, it's concave down. The estimate is an over approximation. And that's really all you have to put for that. So do keep that in mind. Now they want us to find the true value here. And the square root of 9.1, if you type all that in your calculator, believe it or not, you're going to get about 3.0166. So it's a pretty fair estimation there. So the next question would be, would your linear approximation formula be an accurate tool to estimate the square root of 25, and why or why not? And I would say no, because keep in mind, the square root of 25 is really too far away from the point of tangency. Keep in mind that the point of tangency that we had, let's see, what was the value of that point? It was 9.3. So the point of tangency, this is looking at x to be 25, and that is way too far away from our x of 9. So it would not be. And really this is why it's called a local linearity. Is because this 25, x equals 25, is not in the neighborhood of or local to 9.